An open top box is to be made by cutting congruent squares of side length x from the corners of a 20 by 25 inch sheet of tin and bending up the sides. How large should the squares be to make the box hold as much as possible? What is the resulting maximum volume? So first thing we need to do is model the situation so we know what we're talking about. And so it's a 20 by 25 inch sheet of tin. It's rectangular, so it would look like this. So we're going to have a 20 by 25 rectangular sheet of tin, and we create the box by cutting squares out of each corner. So the side length has to be represented with x because they specified that in the problem. And when I model that, it would look like this, where a square would be taken out of each corner and the dimensions of the square would be x by x. And so we want to maximize volume, so I need to represent volume algebraically. So volume equals length, width, and height, length times width times height of a rectangular prism. And so we have to find a way to represent these three variables. Well, the length can be represented as the length of the tin sheet minus the two pieces that are going to be cut out. So L equals 25 minus 2x. And the width can be modeled the same way, but with the 20-inch side. And those are interchangeable because it's multiplication. So I could have represented the length as 20 minus 2x, and the width as 25 minus 2x, doesn't matter. And the height, well, height's going to be when I fold the flaps up after I've cut, that'll be how tall the box will be. So that'll be represented with x. And so when I plug it all in together and use substitution, volume can be represented as 25 minus 2x times 20 minus 2x times x. And there's only one variable with our algebraic model, so I don't have to use any substitution with another formula. It's already done. Only one variable. So now I can take a derivative. So I'm going to solve this problem algebraically. So I take my volume formula, and I'm going to go ahead and distribute the x so that I have two products, so I can use the product rule. Otherwise, I don't really have a rule for three products, and distributing the x is the easier thing to do rather than to FOIL. So using the product rule, the first times derivative of the second plus the derivative of the second times the first. And then in order to maximize the volume, I've got to find the maximum, or the location of the maximum, the x value that will give me the maximum. So I'm going to set the derivative equal to 0. And then in order to solve, I need to multiply everything out. So use the FOIL method for my first two products. And then again, distribute the -2 to get rid of the parentheses for the term on the right. And then I'm going to combine like terms, and I end up with this equation. Now, you can try to divide out some things and factor. You can use the quadratic formula, but more than likely this type of problem would be on a section of the test where the calculator is allowed, since they're such big coefficients. So what I would do is I would put this formula, or excuse me, this equation in my calculator, and I would graph it and then calculate the zeros. So to the left, to the right, and then press enter, and the calculator will estimate where that 0 is. And it's an approximation, so you definitely want to put x as approximately whatever that value is. And don't forget that in AP Calculus we round to 3 decimal places. And there was a second point of intersection, so you also need to calculate that 0. And so then you have two x values that are possible maximums for this situation. Well, one thing we need to do is we need to think about the domain of our situation here. X cannot be less than 0 because x represents a measurement. Also, it can't be greater than 10, because if you think about it, if we cut 10 by 10 inch squares out of each side, you know, your width was only 20 inches, so you wouldn't have anything left. So we're dealing with a closed interval from 0 to 10, and it's a closed interval, so we are testing for absolute max, which we kind of knew already. But what that means is you don't have to use a sign chart. You can just use direct substitution to test the critical values. So this is our situation, testing the values. We won't test the 11.318 value because it's not within our domain. So we're going to test the one critical value, 3.681, and our endpoints on our closed interval 0 and 10. We plug it into our original volume formula because we're finding an absolute, and that's how you find an absolute on a closed interval. So plugging it in for V of 3.681, I got this in the calculator, and it's approximately 820.528, again rounding to 3 decimal places. When I plug in 0, I get 0, which makes sense, because if the length of the squares is 0, then I didn't cut anything out, and I have nothing to fold up to make a box. And then 10, if I plug that in, I get 0, which again, not a surprise, because if I cut 10-inch squares out of each corner, I won't have anything left as far as width is concerned. So, now that we verified that x is approximately 3.681, there's a maximum for the volume function, we have to represent our answer. And this is the point where you always need to go back to the original question to make sure you found all that was asked for. So when we look back at our original, it says, how large should the squares be to make the box hold as much as possible? And what is the resulting maximum volume? So we need two things. First, we need the square's dimensions, and then we need the maximum volume. And it's incredibly important that you make note of what your answer is supposed to represent. So the square's dimensions, and that was the x value that gave us the maximum volume. So it's approximately 3.681 by 3.681 inches. Always include units. And then the maximum volume will be, well, we've already found that. We plugged in that x value into the volume formula, so we know that it's approximately 820.528 inches cubed. Don't forget, volume is cubic inches. So that was all the work involved in solving this optimization problem. And of course, you can always go back and review this again if you need a refresher.